12, 13 people so far. Okay, let's give it one more minute, maybe, because there are supposed to be, I think, 16 people in the class. So we start at, let's say, 10:32. Okay, I guess we can start. So yes, welcome to this course, BIO206. This is the course called Physics and Chemistry for Biologists. And I'll be teaching the first half of this course, which is the physics part. My name is Sushant, and I'm here with the physics department, obviously. Today being the first lecture, let's start off a little light. I'll give you a brief run through of what to expect from this course, or at least from the first half of this course. And then we'll just introduce ourselves briefly. So I'm guessing most of you have already seen the Canvas page for this course. So this is, overall, it's a 4-credit course, of which the physics part is going to be 2 credits and the chemistry part is going to be 2 credits. So we'll work through the physics part, physics and a little bit of maths as well. So physics and maths part for the first 6 weeks, after which Professor Kalyan will take over and he'll do the chemistry part of it. As you probably know, you'll have 2 lectures every week, 1.5 hours each. One is on Monday and one is on Wednesday. And there's also a 1-hour self-study topic. So the thing is, this trimester, because of COVID-19 and everything, and because all of you are constantly on Zoom all day on the screen, we decided to not have very extensive online teaching hours, which is why you only have 3 hours of lectures in this course. So, but obviously, in order to cover all the material, you will need 1 more hour at least. So every week, I'll give you 1 small topic which you can read up by yourself. It won't be a difficult one. I've chosen the topics in such a way, and you can read that by yourself. Of course, if you have questions, you can always come and ask me. That's always there. I've also scheduled office hours for Tuesday at 5 to 6:30 p.m., which is also mentioned on the Canvas page. If there is some sort of clash, if there's something else that you have at the same time, please let me know, and then accordingly I can reschedule it. So look into that, and maybe once the first 2 weeks of the ad drop period are over, you'll know when you have time, when you don't have time. So then accordingly we can fix up some permanent office hours. But for the time being, let's call it Tuesday evening. My contact details are also given on the Canvas page in case you need to ask questions. As far as the course literature is concerned, I have sent you some links and some material. I think that should be sufficient. If not, every week I will also send you some extra links from which you can do some practice problems, some calculations, just to make sure that you're not relying entirely on the class notes. Because, I mean, face it, with just 4 hours a week and 6 weeks, there's not that much that can be covered. So you'll have to make sure that you are doing a substantial amount of reading and working by yourself as well. Don't just rely on what's happening during the lectures. As far as the grading is concerned, we'll have 1 exam in the end that is going to be worth 20 points. I'll give you assignments during the term that will be worth 20 points, and then some short quizzes worth 10 points. So tentatively, this is how I plan to do the grading. But in case something changes, I'll obviously let you know. If you have questions, and I'm hoping you have questions, it would be great if you can either send me an email, or I'll also open an open discussion board on Canvas. So you can use that discussion board. alternately, there are the office hours that you can meet me at. And of course, during the lecture as well. If you have any questions, just unmute yourself and ask me. That's perfectly fine. What else do I want to tell you? I don't make proper notes as such. I just have a few scribbled things on my book, and that's what I teach on the basis of. So I don't have any proper PDF that I can actually share with you. So ideally, maybe you can take notes while you're attending these lectures. Of course, these lectures are all being recorded, so they will be uploaded. And if you want to go back and look at them, that's also an option. But at least in my personal experience, I find that writing things down really helps me retain the information. So it might be a good idea for you to take notes during these lectures. Yeah, I think that's pretty much the introduction I wanted to give you. About me, I said I'm a physicist. My main area of research is theoretical particle physics. And yeah, I'm looking forward to teaching your class. Should we do a quick introduction with all of you as well? Why don't why don't I call out your name, and then maybe you can just for a minute you can unmute yourself and tell me something about yourself and about your interests. So I'm just going in the order by which you appear on the participants list. So Ajit.
Yes. Good morning, Professor.
Hi.
Hi, I'm Ajit. Yeah, and I'm from Kerala. And in Krea, I prefer taking biological sciences as major and environment science studies as my minor.
Great. Thanks. Anupama.
Yeah.
Good morning, Professor. I am Anupama. I am also from Kerala. I am also planning to take a major as biological science and minor as environmental studies and psychology.
Samar.
Professor. I'm sorry, wait. It's echo.
Oh, it's not very clear. Sorry, I can't hear you.
Hold on, the screen.
Oh, I think you're logged in through two devices. So maybe if you move.
Yeah. Is it better now? I was just trying to switch my devices.
Right.
Okay. Hi, I'm Samar. I'm from Punjab, but currently living in Pune. Just shifted here, shifted into this house like a couple of days back. Well, I'm taking a bio major with chemistry minor, and I aspire to be a biotechnologist.
Thanks. Gopika.
Hi, I'm Kopika. I'm from Chennai. I'm planning to major in bio and minor in psych. And my interest lies in stem cell and neuroscience. Thank you.
Thanks. Jeswin.
Yeah, good morning. I'm Jaswin John from Hosur. My native is further south of Tamil Nadu, and I'm interested in the environmental management and sustainability side, and hence I'm opting for the joint major, the Econ EVS joint major. And I feel this course will help me in probably getting an like the physics and chemistry aspect of like the sustainability aspect of it, or at least an introduction to it. So yeah, I'm looking forward to it. Thank you.
Thanks. Kartika.
Yeah, hi, I'm Kartika. I'm from Bangalore. I'm doing a bio major with a psych minor, and my interests lie in infectious diseases and cancer biology, and I look forward to this course.
Thanks. Kaustav.
Hi, I'm Kaustav, and I'm from Chennai. I plan on doing, well, obviously, a bio major given this course and a possible minor in either psychology or chemistry. I'm unsure about that. My interests lie in computational biology and the intersection between biology, artificial intelligence, and psychology. Thanks.
Thanks. Mahesh.
Hi, Professor. Yeah, I'm Mahesh from Kerala, and I'm taking biology as my biological science as my major and environmental studies as minor. So my interest is in the field of genetics. Yeah, that's it. Thank you.
Thanks. Maitreyi?
Hi, I'm Maitreyi. I'm from Chennai. I'm doing my major in biology and I'm considering minoring in politics. I'd like to do public health policy and community health.
Thanks. Nandita?
Hi, I'm Nandita. I'm from Kerala and I'm looking to pursue a biology major and possibly a chem minor, but I'm not sure about that yet. That's it. Yeah.
Thanks. Radhika?
Hi, Professor. I'm Radhika. I'm from Noida. I want to pursue a major in psychology and a minor in biological science. Thank you.
Thanks. Rajat?
Hi, Professor. I'm Rajat from Kerala, and I want to pursue majoring in biological science and minor in possibly psychology. And I'm looking forward to this course.
Thanks. Ritu?
Hello, good morning, Professor. I live in Pune and I am taking biological sciences as my major with chemistry minor. Yeah, that's.
Thanks. Rutuja?
Hi, Professor. This is Rutuja. I plan on majoring in biology with special interest in neuroscience and genetics, with a possible minor in either literature or social science. I look forward to the course.
Thanks. Sakshi?
Hello, Professor. This is Sakshi. I'm looking, I want to major in bio with the psych minor. Yeah, thank you.
Thanks. And Tanay?
Yeah, hi, I'm Tanay. I'm from Delhi, and I'm planning to take the EVS and Eco and joint major. And like I'm doing this course so that it helps me kind of with the sciences part of EVS, and because I've had a science background, so I'd like still like to not still like to kind of stay in touch with it.
Thanks. Is there anyone I missed out? Doesn't look like it. Okay, great. Okay, before I start actually, let's have a show of hands. Do you have the raise hand option somewhere? You do, right? Anyway, if not, just tell me that. Out of all of you, is there anyone who has not done maths in 11th and 12th standard?
I haven't actually.
Absolutely no maths?
No.
Okay. What were your subjects? Did you do any physics?
No. I had commerce.
I see. Okay. Anybody else?
I haven't done math, but I did do physics.
Who is this? Sorry.
Maitreyi.
Oh wait, I thought that was you before. So who said before that they haven't done maths or physics?
Radhika.
Okay. So there are two of you then. Okay. So let me tell you a little bit about the actual material that we're going to be doing in this course. The first 1 to 2 weeks, we'll be discussing mostly maths topics, just some basics of maths. After that, we'll move on to physics. For those of you who have done maths and physics in 11th and 12th, you're not going to learn anything new. This is just like a recap. And what I'm going to do is I realize that most of you are biology students, and I'm guessing maths and physics are not your favorite topics. So as far as possible and up to the limits of my knowledge, I'm going to try and motivate some of these concepts using examples from biology. Like I'm saying, up to my knowledge in biology, which is quite atrocious to say the least, but I'll try. So for those of you who do have a background in maths and physics, this is just going to be like a fun recap of everything. For those of you who have not done maths or physics in 11th and 12th, most of this material will be new. And needless to say, you will have to do a little extra work in order to catch up with the rest of the class. But like I'm saying, you are always welcome to contact me if you need any help, and I'm glad to help you. Email, office hours, whatever. So why exactly should we be studying physics and maths for a biology course? Well, physics has quite a few applications in biology, not surprisingly actually. Just to give you some simple examples, you might want to model the network of nerves in the body or the network of blood vessels, the circulatory system in the body using the kind of tools that we develop in physics. Or for example, let's say you want to describe the electrical impulses that go through the nerves, through your neurons. So again, for that, you might require some knowledge of electromagnetism and so on and so forth. There are lots of various reasons why a biologist should know some basic elements of physics. Of course, there's a whole branch of biophysics, quantum biology, and so on, which are like very happening things these days. So it's always good to have a base in physics. Of course, doesn't have to be very advanced, just some basic level knowledge that to get you through. How about maths? Why should you do maths? Well, very often we need maths in order to do physics. So that's of course one reason, because if you want to do physics, you need to know some basic maths. Even apart from that, you might want to analyze some experimental data at some point. You might want to do some statistical analysis. So in that sense, it's also very useful to have a background in mathematics. So we'll cover some basic maths, real numbers, complex numbers, coordinate systems, how to plot graphs and functions, sequences, series, and their conversions, some basic vector algebra, a little bit about matrices and determinants, and calculus, so derivatives and integration. So this is what we're going to cover in maths. And physics, as and when we come to it, I'll tell you what are the topics that we're going to be discussing. Throughout this course, ask me questions during class, outside class, whatever. Do any of you have any questions so far right now?
Professor, probably about the auditing part of the course. So yeah, maybe some details about the assignments, some overviews.
Just this morning, just a couple of hours ago, all of us got an email from Professor Akhela outlining some new rules regarding audit. So I haven't gone through it in detail myself, but I think the basic idea is that for auditing, you can't just come and attend. You have to do some of the smaller assignments. You don't have to do the exam, but some of the assignments maybe you have to do. So I'm just going to confirm about that, and then I'll let you know maybe in a couple of days, if that's okay.
Thank you.
I think there are 3 of you auditing, right? Is there any? So just when I'm guessing you're auditing, and who else is auditing?
I'm auditing.
Tanay and Nandita. Wait, I'll just make a note of this somewhere. Tanay, Nandita, and Justin. Okay. By the way, a lot of the information that I put up will be on Canvas. So it will be a good idea if you set your notification settings such that whenever some change happens, you can you'll be notified about it. Right. So are we ready to jump into it? Yeah. So can everyone see this? Oh, my voice is lagging. Is it still bad?
No, we can see it. We can see it.
Okay. And can you hear me clearly?
Yeah.
Okay. So there are some more messages over here. Ritu has done PCB. Okay, so no maths. Right. All right. So the first topic that we are going to cover over here is perfect. Numbers. I mean, we're doing maths, so might as well start from scratch. So there are various different kinds of numbers. The very first, most basic kinds of numbers that we encounter are what we call the counting numbers. And these are just 1, 2, 3, 4, and so on. This is of course an infinite set because numbers don't really end. And there's a special mathematical name for this set of numbers, this set of counting numbers. And these are called the, natural numbers. If at any point you want to tell me that my handwriting sucks, please feel free to do that. I'll try and be a little clearer. Now, of course, these are just these numbers 1, 2, 3, 4. There's nothing in between. So there's no 1.5, there's no 3.7, and there are no negative numbers so far. Now, if I want to include the negative numbers and also 0, so now if I start doing, say, minus, so all the way from minus infinity, then -3, -2, -1, 0, 1, 2, 3, blah, blah, blah. Then this is the set of all integers. Still, we don't have the intermediate ones. So we don't have the -2.6s and the 1.3s and the pi's and so on. If you want to include all of those also, if you want to also basically all the numbers as such, then those are called the real numbers. So these are the integers as well as everything in between. So -5.9, 0.2, 1.8, 346.1932. All of these are all examples of real numbers. And then of course later we'll look at something called complex numbers as well. So if I were to draw a Venn diagram of some sort, so the smallest of these sets is that of natural numbers. And then this is included in the set of integers. And bigger than the set of integers is the set of real numbers. And real numbers are included in what we will call complex numbers. So these are all the all the sets of numbers that we ever deal with. Any questions so far? So how many natural numbers or how many integers or how many real or complex numbers are there? Infinitely many. Yeah, because the set never ends. You can keep going on and on. These are all infinite sets that we're dealing with. Okay. Now, what is a good way of representing these numbers? So one very easy way is to use what is called the real line. So the real line is just, think of it as a line that never ends, goes heads on in both directions. And then we put some markings on this. 1, 2, 3, 4, -1, -2, -3, and so on. And of course, also the intermediate ones, which it's not possible to write all the numbers because there are infinitely many of them. So this is called the real line. And every point on this line is represented by some number. So this number might be, let's say, 2.5. This number is -0.2. So one way to look at it is, let's say there's an ant which is walking along this line. And at every point of time, you can tell me where the location of the ant is just by giving me a number. So the ant is over here, you might say the ant is at 4.1. So every location on this line is described by exactly one number. So this is called the number line. Now, in the 17th century, there was this French philosopher called Descartes. And Descartes came up with a brilliant observation. It's the first such observation that at least we know of. So he was lying in his bed and he saw the ceiling of his room and he saw a fly sitting somewhere on the ceiling. And he realized that he can describe where the fly is sitting using exactly two numbers. So if he takes the distance from this wall, and then if he takes the distance from this wall and the distance from this wall, then that exactly defines the position of the fly. No other position is defined by these two numbers. So if you call this x and this y, then you just need one x coordinate and one y coordinate to describe the location of this fly. And this is the birth of what we call the idea of coordinate geometry. So in general, we define what is called the xy plane. This is the point 0, 0. And any point in this plane, you can describe by exactly two numbers. You can specify its x coordinate, and you can specify its y coordinate. So if you look at this xy plane, these two axes divide this plane into four parts, or what we call four quadrants. The first quadrant, the second quadrant, the third quadrant, and the fourth quadrant. In the first quadrant, x and y are always both positive, because here x is positive, here y is positive. So x positive, y positive. If you look at the second quadrant, x is negative, but y is positive. In the third quadrant, x and y are both negative. In the fourth quadrant, x is positive, y is negative. And of course, right in the middle, this is 0, 0. So any point you can describe using these two numbers, x and y. And of course, this is because I was talking about a 2D space. That's why you need two numbers, x and y. If you are in 3D space, so let's say the fly was not sitting on the ceiling, but it was flying around in the room. So it's in a three-dimensional space. Now you need three numbers to define its position, x, y, and z. So maybe the length from one wall, the length from the second wall, and the height from the floor, let's say. So with these three numbers, you can define every single point in the room uniquely. That is the important point over here. This description in terms of these two or three numbers is always unique. And the number of numbers that you need, whether it's xy or xyz, will depend on what is the dimension of the space that you are looking at. Can you think of a 1D space? We've talked about 2D and 3D. What would be a 1D space? Just the real line. The real line itself is a 1D space. Because on this line, you just need one number to define every location. So it's like an ant walking on a clothesline. And if you assume that the clothesline is one-dimensional, then at every point, there is just one number. And you can tell me exactly where the ant is if you give me that one number. Now, because all of this was Descartes' idea, these kinds of coordinate systems where we have x, y, z, or x, y, or whatever, these are called Cartesian coordinates. But of course, there is no reason why we should use only Cartesian coordinates. You can also use other kinds of number systems. So, for example, let's stick to the 2D plane. And we were calling this x and this y. And we said that no matter what point you take, you can define it in terms of x and y, the two numbers. But you can also do it in other ways. For example, you can talk about what is the distance of this point from the origin. So I can call this r. And what is this angle that it makes with the x-axis? So we call this angle theta. So this point, you can also, instead of xy, you can also define it in terms of r theta. And you can just play around and convince yourself that no matter what point you take, it has a unique value of r and theta. So in the same way that each set of x and y define one specific point, also each set of r and theta define one specific point. And depending on what kind of analysis you're planning to do, sometimes it might be convenient to use the xy system, sometimes it might be convenient to use the r theta system. But the important thing is you need two numbers, r and theta or x and y, and that's because you're in a 2D space. No matter what kind of coordinate system you use, whether you're using a Cartesian system or whether you're using this r theta, which is called the polar coordinates, or something else altogether. You don't have to restrict yourself to these two. No matter what kind of coordinate system you choose, as long as you are in a 2D space, you will always require two numbers to define your point. As long as you're in a 3D space, you'll need three numbers to define your point, and so on. So can anyone think of some more examples of two-dimensional spaces? One is, of course, the XY plane, but any other that you might think of? Feel free to unmute yourself and just talk.
Doesn't your tablet screen technically count as a 2D space as well?
Sorry, could you be a bit louder, please?
The tablet screen upon which you're drawing everything that you are, that's a 2D space as well, right?
Yeah, this tablet screen is a 2D space. So in principle, I could draw coordinates on this. Then if you ask me where is the word Cartesian written, I might say 2.3 or 2,3 or something like that. Sure, that's one example. How about the surface of a sphere? For example, like the Earth, the surface of the Earth is a two-dimensional surface. That's why you can walk on it when you go out. Don't go out because there's a virus out there, but it's a two-dimensional surface. And no matter what point you choose on the Earth's surface, you can define it using two numbers, the latitude and the longitude. So every point is given by one latitude and one longitude. So that's a two-dimensional space, on which every point is defined by two numbers. How about, let's say you're doing medicine. Let's say there's an intestine and somebody has an ulcer on the intestine, and you need to describe where exactly that ulcer is. So the intestine is kind of like a cylinder. And then, sorry, this is a really bad drawing of an intestine. Well, maybe this makes it better. And then what you need to know is, what is the distance from the top? So let's call this Z. And then because the intestine is like a cylinder, you need to know where exactly on this angular part it is. Is it at theta equal to 0, theta equal to 90 degrees, 180 degrees, or somewhere else in between? So over here, you will need the Z theta coordinate system in order to pinpoint any point on the surface of a cylinder. So that's one example of a 2D space. How about an Excel spreadsheet? That's a 2D space. If you want to pinpoint any cell, you need to know the row number and the column number, and that tells you exactly where you are. So these are examples of 2D spaces. Any more examples of 1D spaces that you can think of apart from the real line? How about the surface? How about a circle? So a circle, every point on the circle you can define by just one number, which is the angle. So let's say if I start from here, if I call this 0, then every point I can define by this angle. So this is going to be, let's say, 48 degrees or 132 degrees or whatever. So I'm just talking about the circle itself, not the interior. So if there's an ant walking along this circle, you can always say, okay, the ant has moved from 33 degrees to 36 degrees. So this is also a one-dimensional space. Difference between this and the real line is that this is not an infinite one-dimensional space. This is a finite one-dimensional space where this theta goes from 0 to 360 degrees. In mathematics, often we don't like to use degrees. We like to use another units for angles called radians. And a radian is defined as the angle so a radian is the angle that is subtended 1 radian such that the length of the arc that it subtends over here is exactly equal to the radius of the circle. So this angle is 1 radian. And there's a very easy way to convert between degrees and radians. So if you have angle in degrees, you multiply it by pi over 180. This gives you angle in radians. And of course, the other way, angle in radians. You multiply this by 180 over pi. This gives you angle in degrees. So we use radians extensively. Any questions so far?
Professor?
Yeah.
Given how between any two real numbers you have infinite number of real numbers, doesn't the same thing apply with the number of angles within the finite set of the number of angles in a circle?
Absolutely. So, okay. Okay, sorry, I should specify. I don't mean that this set of angles is a finite set. What I mean is that it is bounded. So it's only between 0 and 360. Of course, within this range of 0 to 360 degrees, there are infinitely many angles. So you can have 1.2 angle, 1.2 degrees, 1.3 degrees. Within that, 1.25, 1.26. Further, you can go down. So of course, there are an infinite number of angles within this range. Yeah. Thanks. Any other questions? Those of you who have not done maths, is this going too fast, or are you at least being able to catch some of the basics?
No, this is fine.
Okay. Great. What time is it? 11:09. Okay, why don't we take like a 5-minute break and we meet at 11:14? Yeah. So this is the one example of a linear function. Of course, like I said, a linear function doesn't always have to have a positive slope. It can also have a negative slope. It can have a graph that looks like this. Can you give me an example of some dependence which has a negative slope? Tanay, I will answer your question in a bit. Any example that you can think of? How about incidence of a disease versus percentage of population that is vaccinated. So if more people are vaccinated, then the incidence of the disease is lower. If fewer people are vaccinated, then the incidence of the disease in society is more. So this is one example of a function that has a negative slope. Okay, let's look at Tanay's question. Will regression lines work on the same principle, since the two variations in regression are not based on causation and can essentially be any two random things with their own friends? That is true. So even if there is no causation, if it is just a correlation between some two variables, it will still look like a straight line. That is true. But as you're rightly saying, just because there is this trend doesn't necessarily mean that there is a causal relation between the two. Correct. So those were linear functions. How about reciprocal functions? Reciprocal function is y equals 1 over x. This looks like this. So when y is very small, when x is very small, y is large. When x is very large, y is small. And of course, this happens on the positive side as well as on the negative side. Possible examples of this. So on the x-axis, you could plot size of a herd of zebras. On the y-axis, probability of being caught by a predator. So that's why these animals always tend to prefer staying in big groups. The larger the size of the group, the smaller is the chance of any one of the zebras being eaten. Any questions? Please stop me at any point. You don't have to just type in the chat. You can also unmute yourself and start talking. That's fine. What about quadratic functions? No, I did not ask for this. So these can, so in general, quadratic functions always look like parabolas. So you can, of course, y equals x square looks like this. But you can also have y equals minus x square. You can have x equals y square. And all kinds of such shapes. One very useful quadratic function, which features in studies of ecology, is what is called the logistic map. Damn it. So this has the form y equals x minus x square. So this is also one possible quadratic function. So the reason I bring this up is that, for example, on the x-axis, if you have the population, suppose you have some small island with very limited resources. On the x-axis, you have population in this generation of rabbits, let's say. And on the y-axis, I plot population of the next generation. So of course, in this generation, if there are very few rabbits, then in the next generation also there will be very few rabbits. And it keeps increasing. And there is an optimal number. If the population of rabbits in this generation is over here, then you have the largest possible number of rabbits in the next generation. But if you have far too many rabbits, then they're consuming all of the resources, which means that the population will again start dropping. So this kind of map is quite interesting in trying to model the propagation of various species when resources are limited. Then there are exponential functions. Examples of exponential functions? Very current example. About the spread of a pandemic, exactly, COVID incidence rates. So you have one person who has COVID-19, and then they spread it to 3 people, and then each of these 3 spread it to 3 more. So this becomes 9. And then if each of these go and spread to 3 more, it's going to become 27. So first it was 3 to the power 0, then it becomes 3 to the 1, 3 to the 2, 3 to the 3, and so on. So in general, after n such steps, you will have 3 to the n people already infected. So this kind of function is called an exponential function. So x, y is some a to the power x. So in this case, in this example that we took, a was 3. In general, it can be anything. The most commonly used base of the exponent is e, which is Euler's number. It's a special number because it has a lot of utility in doing calculus. E has a value of 2.718, blah, blah, blah. It's like pi. It's a transcendental number, and it's a very useful number. It's used extensively. What other functions do I want to discuss? How about the power law function? Power law function looks like x to the power n. Any examples of power laws? How about, so, okay, here's one example of physics application in biology. Intensity of light with respect to distance. Yes, that goes as x to the power minus 2, correct? So one, okay, this is going to start like the sound of a bad joke, but suppose I approximate a human as a sphere, okay? Consider ideal spherical humans in a vacuum of radius r. Now, the amount of heat that your body produces is proportional to the actual amount of matter that you have inside you. So that is proportional to r cube, because volume of a sphere is proportional to r cube. So the amount of heat that your body generates is proportional to your volume, which is r cube. But how about the amount of heat that your body loses? Your body loses heat by radiating from your surface. So the amount of heat that you lose is proportional to the surface area of your sphere. And surface of area of a sphere is 4 pi r square, so it is proportional to r square. So total heat that is left in your body is what you have gained minus what you have lost. And if you plot this function, you will see that for large values of r, the total heat is more. For small values, so because for large values of r cube is more than r square. Let's plot it. So if r square looks like this, r cube will look like this. So for large values of r cube is more, but for small values of r square is more. This is why people who are bigger, people who have more muscle, fat, etc., tend to feel more hot, and people who are skinny, small, they don't feel as hot because their body is more efficient at losing heat, whereas those who are bigger are more efficient at generating heat. So yeah, this is a good example of how you can use some very simple physics and maths considerations to try and explain a biological phenomenon. Even though humans are not spherical and in a vacuum, this argument still holds. Any questions? Another power law is the log word frequency of words in natural language corpus. Yes, that is true. If you, do you know more about this? Can you tell more?
Sure. It's called the Pareto principle, and let's say you plotted the number of word incidents in any natural body of text. So say you took your favorite storybook and you plotted the frequencies of every word that occurred. The second most common word will be half. The second most common word will occur half as many times as the first most common word. The third most common word will occur 1/3 as the first most common word. So it follows a harmonic sequence. And when you plot the log-log relationship of this, you get a power law that describes the number of words with respect to the first most frequently occurring word.
I see. So when you're saying half, 1/3, is this on a log scale or linearly? I mean, I'm not getting where the log is coming from.
It's a linear scale. So when you plot the linear relationship of just the absolute number of frequencies, you get I mean, I don't know how to describe it, but it's like the first quadrant of a reciprocal function.
I see. Interesting.
That's
Okay.
vaguely how the shape is. So when you take the log-log relationship of the same linear function, you get a straight line, which represents a power law.
I see. Thanks. I'll definitely look this up. Okay. Let's look at some more functions. Since you mentioned log, let's look at the log function. Log is simply, what did I do now? So log is defined as if you take the product of two numbers, then the log of the product is just the sum of the log. this is the basic definition of the log function. So this is confusing if you haven't seen this before. So if I plot the function log of x, log of 1 is always 0. And then it increases very slowly as you increase x. Log and exponential are opposites of each other. So if y is e to the power x, then x is log of y. This is for logs, you can have different bases. You can choose any base you want. So this is in general, if y is a to the power x, then x is log of y to the base a. Okay. How about some trigonometric functions? So the trigonometric functions are sine, cosine, tangent, and their reciprocals, cosine, cosecant, secant, and cotangent. What do these look like? This is what sine looks like. Cosine has a phase difference with this of 90 degrees. What did I do? Oh. Sorry. And tangent, of course, goes all the way to infinity at 90 degrees. So I should probably put down some marks over here. This is 0, this is 90, this is 180, and so on. Tangent at 90 will blow up. And so on. So you've probably seen trigonometric functions extensively before, even in your school, in your 10th standard or so. And there are a bunch of trigonometric identities which one can look at. For example, sine square plus cosine square is always going to be equal to 1 no matter what. I won't really discuss trigonometry, but I will assume that you know some amount of it, because otherwise it just becomes too much of material to cover. Finally, I want to talk a little bit about complex numbers. How much time do we have? We have 7 minutes left. Do any of you have any questions? Okay, so let me then quickly I'm going to erase this. So I'll quickly introduce complex numbers. So sometime back, I said that if you take the function x squared plus 4, and if you want to try and find its roots, there really are no roots. And there's a simple reason for that. The reason for that is that if you take the square of a number, it's always positive. So 0 square is 1, 1 square is 0 square is 0, 1 square is 1, 2 square is 4, 3 square is 9, and so on. But also -1 square is 1, -2 square is 4, -3 square is 9, and so on. So square root of 4 can be +2 or it can be -2. But square root of -4 isn't quite defined. So you can say that square root of -4 is just square root of 4 times -1, which is square root 4 times square root -1. Square root 4 is fine, that's 2. But this square root -1, which really doesn't make any sense, we give it the special symbol I. And we say we'll call I an imaginary number. So I is imaginary. And in general, you can write a complex number as a real number plus an imaginary part. So A and B are both real numbers. When you do IB, then that becomes an imaginary number. And then A plus IB is a complex number. As you can see, complex numbers, they contain real numbers within themselves. Because if I just take B equal to 0, then Z just becomes A, which is a real number. So complex numbers are a superset of real numbers. If I give you a complex number Z, then we say that the real part of Z is A. We say the imaginary part of Z is B. And we define what is called the complex conjugate Z star, which is A minus IB. So if you start with A plus IB, then the complex conjugation just reverses the sign of the imaginary part. You can't see my screen. Is that a problem with everyone? Can nobody see my screen? Okay, Rutuja, then maybe it's some problem at your end. What can I do with complex numbers? How can I keep forgetting that. What kind of operations can I do with complex numbers? So I can always add them. So if I have 2 plus 3i as one complex number, and I want to add this to -1 plus 4i, then it's straightforward. I can just add up the real parts and the imaginary parts. So 2 and -1 gives me 1, and 3 and 4 gives me 7. So this is just 1 plus 7i. Same with subtraction. What about multiplication? Let's see if I want to multiply these two numbers. If I want to multiply 2 plus 3i multiplied by -1 plus 4i, then you just treat this as you would multiply any algebraic expression where I was replaced with x or something. So this would be 2 times -1, which is -2. Then 2 times 4i, which is 8i. 3i times -1 is -3i. And 3i times 4i is 12i squared. Now I square, of course, is -1 because that is the definition. So this is just -2 minus 12 plus 8i minus 3i, which is -14 plus 5i. So that's how you would multiply complex numbers. How would you divide complex numbers? Let's say 2 plus 3i divided by -1 plus 4i. This is where this complex conjugate becomes useful. you can multiply and divide by the complex conjugate of the denominator. So you do -1 minus 4i minus 1 minus 4. Now you will find that if you multiply a number by its complex conjugate, you will just get a real number. So in the numerator, you can do normal multiplication of the kind that we did over here. And the denominator will just become a real number. So that defines your division with complex numbers. Okay, any questions so far? We've come to the end of the class. If you have any quick questions, we can take them now. Otherwise, we'll meet next time. So, questions? Okay, so if not, we'll meet, I think, on Wednesday. And I think I have already uploaded like one set of extra reading that you can do this week. If not, I'll upload it now. And of course, tomorrow is Tuesday, so tomorrow evening is when we have scheduled office hours. If you want to ask some questions or discuss something, feel free to meet me on Zoom at that point. I'll send you the Zoom link for that. Any instances of complex numbers in biology? Yes. So complex numbers are often used in describing electrical signals and light signals. So if you're doing anything with, let's say, electrical impulses going through your neurons, or let's say the light response in your retina, and then you might have applications of complex numbers in that. Yes. Any other questions? Do we have complex functions? Yes, absolutely. Sure. If you have another class and need to leave, please go ahead. Officially, the lecture is ended. Complex functions, yes. Just as you have defined real functions, you can also define complex functions in the same way. Okay. So thank you all, and see you soon.